because what you, the unsung heroes in the wastewater industry, do matters. Every Wednesday, join me, Suzanne Chin Taylor, the DooDoo Diva, a longtime veteran of the wastewater, trenchless, and civil infrastructure industry, as I interview guests who are making an impact on how we manage and operate systems for conveying and treating wastewater. I'll also be speaking with representatives of organizations that are utilizing disruptive or new technologies, and executives who are going to share how to be successful and sustainable in our vital industry. So whether you want to learn about the latest trends in technology in treatment or trenchless, gain tips on training and retaining great talent, or simply how to be more efficient, productive, or profitable, this podcast is for you. Well, good afternoon and welcome everybody to this week's episode of the DooDoo Divas Smells Like Money podcast. I have the distinct privilege of visiting today with Dr. Joe Royer, PhD, who is the Vice President of R&D at, and please excuse me, Joe, if I really mess this up, of GeoTree, which is part of the ClockSpring NRI group of companies. Did I get that right?
That is correct. I'm head of R&D for all of them, including GeoTree.
Oh, all right. Well, thank you for the correction.
It's too confusing anyways, don't worry.
Okay, great. Well, what we're going to focus on in today's episode is geopolymers and their applications for wastewater. And, Joe has a long history with using these in all types of other applications, but we're going to focus on wastewater applications. And, for many of you, you know that I've written quite a few articles on the application of, polymers, polyurethanes, epoxies for wastewater rehabilitation and trenchless. But this is something that's very new to me. And this is why it kind of piqued my interest. And I wanted to bring Dr. Joe on the show just to discuss this particular option for wastewater structure rehabilitation. Many people may not be aware of it. They're more comfortable or have more, information on their desk or been more exposed to epoxies and polyurethanes. And so with that said, Dr. Joe, can you give me a little bit of history on geopolymers and, what we're talking about today and how they compare and contrast to epoxies and spray applied polyurethanes so that people can create that contrast in their mind and understand this?
Absolutely. So the first and probably most important thing is to define a couple words that probably get misused a lot. So the first word I would think of is to define the word polymer. So polyureas and epoxies and geopolymers are all classified as polymers. What that means is polymer is a combined word that means many mers, and mer is basically small change. So you basically could think of a really, really, really long molecule as a polymer. Okay. So the second thing that people think, and this is probably a little bit of a misnomer from how people think about these things, but people think the word plastic and they think the word polymer and they think they are the same thing. Okay. So HDPE, polyethylene, polypropylene, epoxies, polyureas, those things are all polymers. And plastic is really a way of defining their physical characteristics, but not necessarily their chemistry. And geopolymers are what we would refer to as inorganic polymers, which means they don't have much carbon, where all of those other things have a lot of carbon in them, and they're organic polymers. And inorganic polymers have they can be rigid, they can be brittle, they can be flexible, but they're generally what you think of when you think of a plastic. It's an organic polymer. An inorganic polymer, like a geopolymer, does not look like a plastic at all. It looks a lot more like a cement. So it has the properties of cement, it's got the flowability of cement, but it's got the chemistry of a long chain molecule, which makes it more like the chemistry of a stone or a quartz. And that gives it really good chemical resistance properties, which makes it useful in wastewater applications. Did any of that make sense?
Absolutely. You know, I think I shared with you before the show, my father was a PhD in chemistry, taught on the university level. So some of the things you were mentioning are things that I remember from, you know, being at his knee and hearing this spoken about, but the difference between inorganic and organic. And so as we're thinking of this for applications for wastewater structures, one of the things that you mentioned is that these types of polymers can be more competitive for certain applications. And so now we're getting a handle on what makes them different, but now we're used to spray applied. How are these applied? Are they troweled on? Are they, you know, brushed on? Can they be spray applied? How are they applied to the surfaces? And then also, what type of prep and installation considerations come into play with this versus some of those other, you know, formulas or materials that we're very, very familiar with and very much used to?
Yep. So in the wastewater treatment facility, people are used to spray applying these polymers onto concrete walls.
Right.
So you can think of the geopolymer as the replacement for the concrete wall, or the build back if you've got corrosion. And depending on that case, you can put a polymer coating on top of that. And now the material underneath it has got a better corrosion resistance. But they can be troweled on, they can be spray applied, they can be used in more of like a shotcrete process. They can be used with steel reinforcement if you're embedding that into the wall of a treatment plant. But for people that are used to repairing sewer interceptors or the large diameter pipes that are involved in sewage collection and movement to the treatment plant, this is, you know, the polyureas and epoxies don't tend to be very cost effective there because they're large areas and they're long pipes. And so these materials are the predominantly used spray applied systems in large diameter pipe repair, specifically in sewers. And they've been used to some degree in wastewater treatment facilities, and especially in the piping in those.
Okay. Okay. So when you were talking about it can be applied directly, where I know some of these other materials, you know, we say the key to a successful application or project are the 3 Ps: prep, prep, and prep. And so how does it compare in using this material when we're talking about prep for application?
So I would agree with that statement. They all require that difference. So these materials are more cementitious, or they're cementitious in nature. So what you're going to want to do is you're going to prep it like you're prepping for a cement. So you can have pretty heavy aggregate visibility. You're going to want to get your material down to as good of a concrete as you can if it's been corroded. You're going to want to stop active water flow so that there's infiltration, which is not that common at a waste treatment plant, but it's very common in the piping world. You can't have flowing water, but the best scenario is for that entire structure to be basically clean and damp. So you can pressure wash it, is typically what's done with a 3 to 5 to 10,000 PSI pressure wash. Get all the loose material off, back to good concrete. And while it's still wet or with a fresh, damp coat, you can apply these materials.
Okay.
The difference between that and what you're going to call your traditional plastics is we're going to prefer to be wet to get a good bond, where they're going to prefer and in most times require that the concrete that they're going to be applied to has been sitting for 28 days or so to be cured if there's a build back coat. And they're going to require that that concrete be pretty much bone dry in order to get a good bond. And so you can pressure wash and we can go right over that and be wet. And then the reality is, if you want to apply an epoxy or a polyurethane to our material on top of that, you could do that much quicker than you could do it with a normal cement, because we're going to build about 70 to 80% of our strength in the first couple days. So where you might have to take a treatment tank down for a month to do a rehabilitation on it, you might be able to do that same thing in a week.
Well, that brings up an interesting point when you said that. So you could apply your material at however many mils thick, but then they could come in and apply another polyurethane on top of that in just a thinner coat for whatever reason. Is that a common practice, or can the geopolymers just kind of sit on their own? Do they really need that additional type of material placed on top of it for the same effect of building polyurethane at, let's say, it has to be 150 mils thick?
Right. So I would say, first of all, we typically don't talk in mils. We talk in, some sort of inch comments.
Okay.
Primarily because, let's say you're in a wastewater treatment plant that has been in the ground and they've been using tanks or whatever for 50 years. And those tanks started out as 12-inch thick concrete walls. And now they're 10-inch thick concrete walls.
Okay.
And the next inch is starting to corrode. And when you pressure wash it, it goes all the way down to 9 from the original 12. So your first step in preparing that, whether you're using a polyurethane or you're using a geopolymer, is you are usually building back that wall thickness to the original design. So typically a geopolymer is going to cost 20 to 30% more than the regular Portland cement on a per pound basis as the build back material. But it's going to be, you could probably put 3 inches of that material in for the same cost of putting 150 mils of polyurethane. And if your original wastewater treatment plant was just built of regular concrete, the geopolymer is going to be at least 2 times, if not more, chemically resistant than that cement. So it's going to be, if you had a wall loss of 3 inches over 50 years, you're going to expect less than an inch of wall loss over the next 50 with the replaced material. You can't put, if you put a polyurea or epoxy coating, that coating's probably still going to be there in 50 years, but it's going to cost you twice as much to put it on day 0, which may or may not be what you're looking to do.
So what I'm getting from this is an alternative for those larger structures that have lost a lot of their substrate, that need all that build back, that which brings me to the question of cure times for this when you apply it. It seems like it's actually more cost effective depending on the type of the project, but what about disruption and setup and return to service? How does it compare to some of the other trenchless methods that are out there right now?
That's a good question. So if you're talking about spray applied systems,
right,
I'm going to say, in my experience, most of the Portland based shotcretes require at least 24 hours cure before you can put them into service.
Okay.
Many of the epoxies and ureas, the substrate that they're being applied to has to be prepared and cured.
Right.
And that may be a significant period of time, weeks or days. But once that material is applied, you can generally go back into service within hours of the system. With geopolymers, our experience has typically been as soon as you can walk on it and not leave a footprint, which is typically, depending on the temperature and the humidity, somewhere between 2 if you're in Houston on a normal summer day, all the way to 6 if you're in, Michigan on a day where you're basically above freezing, but not much. You can, as soon as you can do that, you can put water back on it. So in traditional pipe applications, people are often pulling the bypass every day. So for example, there's projects where you're working on a sewer. I can think of some in downtown Washington, D.C., where they were working on the sewer. They were only doing night work. They had to be totally off the site at 6 a.m. every morning, and they could start back up at 8 o'clock at night. So they would basically plug the pipes, work on the repair, stop by 3 in the morning so that they could pull the bypass at 6 a.m. and release the flow. And then they would go back the next day and continue the work. They might not have finished that whole project in one night. I'm sure they didn't, because it was 24-foot pipe, so they were in there for quite a while, but they can do that kind of work.
Okay. So when we're talking about application for ambient temperatures, I know sometimes that can really wreak havoc, and applicators who might be listening to this thinking, this might be an interesting material to start offering my, my trenchless rehab clients. Any considerations there?
For applying at ambient conditions?
Yes.
Ambient conditions are wonderful. So we like moist pipes, moist structures, not flowing water. And you can generally apply this anywhere from, like, say 35 to 40 degrees Fahrenheit, all the way up to 100 degrees outside. The difference is going to be if you're applying it at 35 degrees and you want adequate cure times and long pumping distances, you might be heating the water that you're using as your mix water.
Okay.
In the 100 degrees, you are definitely going to be cooling that water to 65 to somewhere between 60 and 80 Fahrenheit so that it doesn't kick off. But if you're working in a chamber where you're mixing very close and only pumping, say, 100 feet, you can get away with a lot of things, versus in a pipe where sometimes you're trying to pump 800 or 900 feet, you have to be a little more careful with the cool water. But these things are applied all day, every day around the country in whatever conditions people are working in, as long as it's not raining.
Okay, great. That's good to know. As far as asset life extension, if someone's using this for rehabilitation, how many years can they possibly expect?
That's a great question. I would say the industry standard for all products, and what pretty much everyone tries to do, is give you a 50-year design life. Right. The struggle, of course, is, I would say, the polyurea and epoxies are going to give you that kind of life in terms of corrosion resistant, as long as you get a really good bond to the structure behind it and you don't have any access to the structure behind it. And they'll probably get you a little more than that. These materials, what we would first ask you is, what's your existing conditions that you have? How much material have you lost? And if it's a concrete structure, we're going to be able to say, look, we have a lot of good data to show that we're at least 2 times better, if not more, than those normal things. So we would design your structure to basically give you that lifetime. And then these can be repaired the same way. If you want longer lifetime, you can do that. And there's been a lot of work in Australia associated with real live sewer flow conditions where some of the H2S concentrations are the worst, where they've got some decent models on life expectancy and other things that we can rely a little bit on. But we would, no one's going to do a design that's less than 50 years, with a few exceptions. And those are the projects we always get involved in, because usually it's like someone put a brand new reinforced concrete manhole in 10 years ago and it's mostly gone, and they have no way to shut the system off, and they have no way to get in and clean it, and they just want to do something, and they know they're going to have to come back 5 years from now and do it again. So they're looking for, in that case, the epoxies would be a plastic liner or an insert would be a better case, but usually there's some constraint that prevents those things from being used, primarily access time or ability to clean or some other thing that somebody will just apply ours and cross their fingers. But that's we usually, if they were getting 5 years with what they were doing, we'll get them 10, but that's the other concern that we have on some of those really crazy, 300 ppms of H2S kind of job.
Right. Well, then let us talk about, because there isn't one magic silver bullet out there that can cure all of wastewater infrastructure's issues. So it's picking like the right tool for the job. So if you were to identify the quote unquote, as I say, the sweet spot for these materials where they can be highly effective and highly cost effective, not only are they going to do the job for the rehabilitation, reinstating the integrity of the structure, or, if it's new and they want to do, a prophylactic kind of, let's protect this against the caustic elements that are going to come to this structure so that it can extend it even further. What would you say are those places where GeoTree and geopolymers can really, really shine?
So our normal market is large diameter stormwater and wastewater systems. So typically what we would say is, the predominant technology in pipe rehab is cured in place pipe.
Right.
And we sell to contractors. We don't do any of the work ourselves. And almost all of our contracting partners do CIPP. And what they'll tell you is typically our products become cost neutral. So they're equivalent to the cost of CIPP somewhere between 42 inches and 60 inches, depending on where in the world that pipe is, how big or we know how big it is, how long the run is, what the access conditions are, and the economics of that particular contractor, whether they're making their own cured in place bags or things like that. Almost always at 60 inches and above, this is going to be the most cost-effective solution in a large diameter conveyance pipe. The smaller the pipe becomes, we've done a lot of work in 30 and 36 inch pipes, but generally those have what we talked about earlier, really interesting or really constraining time constraints where you only have 8 hours a day to work on this job. You can't do a 30-inch, 200-foot lining of CIPP in only 8 hours because it takes 24 hours to cure the liner. Mm-hmm. So once you start, you can't stop. If they want you to be off the road that night, you really can't do that, right? So there are some constraints, large bends, large curves, access constraints, because the equipment to do this can be very small. It can fit down, in theory, the equipment can fit down a 14-inch manhole. I'm not sure you could get anybody else down there if you had another piece of access, but these are typically man entry repairs. So there are, the reality is anything large diameter pipe is where we would normally look at it. And I would say where you have significant corrosion and build back, where you're going to want to have a material that's going to give you longer life than your normal concrete repairs.
Okay. So there's obviously process water industrial applications for this. as well. I was thinking about manholes, but it just seems in comparison to other things, it probably would not be cost effective for, your standard manhole repair
It's
or oil.
usually, I mean, to be honest, 150 mils of polyurethane or 150 mils of epoxy in a manhole require twice as much prep, and the material cost is probably 20x that per pound of the materials. So it becomes a very effective, I mean, it's used in manhole technology all around. I would say if you have the worst case manholes where, it's the worst part of your system and you've got the most corrosion, you're going to want to have a second, we feel like these materials will work for those things, but a lot of people have spec'd epoxies and ureas, and they work as long as you get the perfect application. If you get material behind them, you have a lot of trouble. So if you want to have a second barrier, putting our materials behind those things will give you a good benefit. Also, a lot of times when you're doing an epoxy or urea coating of a manhole, they're still having to build back the structure, and they have to build back the structure and then come back and put the coating on after that structure is cured. And generally we're a one-step process. So it can be cost effective in manholes. So there's a lot of manhole work that's been done. But the primary focus that we've had is, long runs of pipe repair.
Large diameter pipe repair.
Large diameter, yeah. Okay. This is not a technology for 24-inch or 6-inch. It's, there are much more cost-effective ways of doing that.
Right. That's why I was asking about the sweet spot. And so this has been really eye-opening to learn about another alternative for large diameter, because there are a lot of lines that need to be repaired. And obviously CIPP, even some of the large, UV CIPP, which they're getting up into the 60 and the 72. But this is a nice alternative to know about, because sometimes it's hard for them to do any type of repair on diameter that large, especially with corrosion, which I just wanted to make sure that we related this to the audience. This can be applied to all types of substrates, metal, corrugated, concrete. Can you, lay those out?
So
okay.
You can absolutely apply this brick, other masonry, reinforced concrete, unreinforced concrete, corrugated metal. You can do plastic, although most people aren't repairing plastic pipe and it's a little more complicated to do, but it's been done like 48-inch, 60-inch HDPE repairs where there was some poor backfill or some other issue. But yeah, this is an alternative to those things. If you're doing a 72-inch CIPP traditionally, you're doing an over-the-hole wet out. You have an entire chemical plant out on that job site, and you're probably taking up, half a football field worth of ground space. And in theory, we can do it. The footprint of all the equipment could fit in the small office I'm in right now.
Wow. Well, so now this brings me to another question, because it's a big thing that's come out, especially when you're dealing with stormwater conveyance and rehabilitation, is the styrene emissions. That it became a big, controversy and thing that everybody was talking about, so that UV CIPP seemed to be the better route for the large storm lines, because they wouldn't have to worry about the bypass or anything getting into the watershed. How does this work with this material? Any chemical concerns when we're dealing with stormwater drainage?
So we're not, all of our materials have drinking water approval for immediate return to service, although no one would ever actually do that. They would be required to do all kinds of other things, but it has that. I certainly do not want to step into the controversy of
not asking
styrene and CIPP. I mean, there's a lot of good work at NASCO and what the ways of abating those things are. But in general, these materials are, they would call there are no solvents based in this. It's water and cementitious materials. we've done some good work to show, with very, very small water rates, the pHs don't affect fish. We've got work in California. We've got drinking water testing and a variety of other things. So these are generally more environmental friendly than any of those technologies. But
yeah, just because I figured that might be a question that would come up because we were talking a lot about CIPP. People are worried about the environment and the applications and not making sure that I'm not doing good and creating any, after effects and harm after I do this. So yeah, thank you for letting me know that and answering that question.
And these materials are typically made of a significant percentage of what we would call post-industrial recycled materials.
Oh,
so
nice.
They're being used as byproducts of coal fly ash facilities. So the fly ash materials, they're using them as reactive components, not just fillers, metal slags and other things that come from steel processing. So there's a variety there can be some natural materials. All of these things would be considered, the term would be pozzolanic, which someone can Google and figure out what it means, but starts with a P and has two Z's, but it's not basically it's a way to make these materials, and those are the reactive components. So there's a lot of environmental benefits to this versus normal cements, which are obviously kiln process and high temperature and a generator of CO2.
Wow. Well, Dr. Joe, thank you. You have just been like a fountain of knowledge. I've certainly learned a lot during this conversation and opened my eyes up to some other technologies, and looking forward to learning more about applications and how people are using this out in large diameter collection systems and wastewater treatment plants. So I do want to thank you for your time today and sharing all your knowledge. And for those of you who are interested in learning more about this technology, you can visit Dr. Joe's company website, which is, and I have to refer to my notes here, it is C as in Charlie, S as in Sam, hyphen, N as in Nancy, R as in Richard, I as in idea.com. And you can connect with Dr. Joe Royer, PhD, on LinkedIn. Again, he is the Vice President of R&D for the ClockSpring /NRI group of companies. And again, Dr. Joe, thank you. And we look forward to seeing you again on another episode of the DooDoo Diva Smells Like Money podcast. And until next time, keep it flowing. Thanks for joining me, the DooDoo Diva, on this week's episode of Smells Like Money. Be sure to subscribe to the show so you'll never miss an episode. And while you're at it, if you found value in this show, we'd appreciate a rating on iTunes, or simply tell a friend about the show, because that would help us out a lot too. If you're an industry expert and would like to be considered as a guest for the show, email guest@smellslikemoneymedia.com. Tell us a little bit about yourself and the topics you'd like to talk about, and we'll be in touch. For more information about our family of marketing, international business development, and workforce training companies dedicated to the empowerment and education of our industry, call us at 760-217-8010 or email me at raven@creativeraven.com. Until next week, a big shout out to all my industry friends and those who will be. You're my superheroes.